Good morning, this is Professor Elliott, and today we are going to look at the NPN voltage divider bias, and specifically the shortcut method. Traditionally, I have taught what I call the standard or the long form method using the base to emitter current model, and by far it's the best method. There's just no argument on that. During the past couple of years, because of the online teaching situation, I have temporarily transitioned to the shortcut method, which is widely taught as well. It's very popular with in electrical apprenticeship programs. It's perfectly acceptable for like troubleshooting or simple quick calculations. It's not good enough for design or work, or if you need real detailed, accurate results. It just won't work. The primary downflaw with it is that it ignores the use of beta DC, the current gain. And one of the key advantages of using the voltage divider, now we're only looking in this video at the NPN voltage divider, but of course there's the PNP. The PNP transistors more or less work with negative supply voltages, but that isn't exactly always 100% the case either, because you can use NPN transistors with negative supply voltages, just bias it in the right way. For right now, we're just going to stick with the shortcut method. If you're interested in the long form method, then please see my YouTube video on NPN voltage divider bias, and in that video I use the base to emitter current model, which works very, very well, assuming the circuit is well designed, which I select values to ensure that they are. For test purposes, it doesn't matter which one you use. You're going to get results that are very similar to one another. But anyway, it's a method that makes it easy to understand. You're only getting part of the picture, but at the moment, I think it's the most effective method to present this topic. But once I go back in class in September, my intention is to going forward is to just actually include both methods side by side, so students can see, which I've kind of done in the past. But anyway, just kind of rambling on here, so let's just kind of get on with it, shall we? Okay. All right, shortcut method. Okay, so why use it? Okay, so as I said, it's a turn my pen on, sorry. It's a simple method to bias a BJT to achieve a stable Q point. Okay, so this is why we want to use the voltage divider. Okay, we can say that when we explored the simple or basic bias, whatever you want to call it, biasing method earlier, we noted how susceptible the Q point is to changes in the beta DC. And if you recall, we also noted that beta DC is the DC current gain. It's the relationship, the ratio between the collector and base currents. And that it varies widely from transistor to transistor. And we saw that if you're up in the active linear operating range, that's sort of the threshold when VCE is greater than 0.7 volts. Okay, it's, as I said earlier, it's a bit of a fuzzy line. It's not an absolute line, but that's what they call it at. The current gain, can be 70, 80, 90, 90, 300, somewhere in there. And as you pick transistors, out of the bag or off the reel, and you put them into the circuit, you generally want the circuit to perform as intended. And with the simple bias, we saw that if we change the assumed beta, the Q point, which is the intersection of collector current IC and collector emitter voltage VCE, very dramatically all over the place. So, for that method is totally suitable to use, in a switching application, where you basically want to either cut off or saturate the transistor, or oftentimes in the active area, but the beta is not such a big deal because you can design around it. When you're looking at a linear AC amplifier, big changes in beta can pose serious problems. And what we don't want to have is, you don't want to have a very unstable Q point, and which causes the signal to distort and clip. That's not what you want. So you need a biasing method that, for the most part, fixes the Q point at the desired point on the load line, irrespective of what the actual beta is. It's not perfect, but it's pretty close to perfect. It does a very good job at self-correcting itself if the beta changes. And the beta will change. Just changes in temperature will cause the beta to change. So anyway, for a BJT, the two biasing methods that you'd use for an amplifier where a solid Q point is critically important is the voltage divider, which we're looking at the moment, and the emitter bias. I think I'm going to go back to teaching emitter bias. We taught it for many years. I've dropped it for a few years, but because we no longer do that in the lab. But anyway, it's an interesting circuit. It's actually technically um, more stable than than the voltage divider. We used to do a lab where and the students no longer have them, so it's kind of impractical. They had a soldering iron, and you just heat up the transistor with the soldering iron for a bit, and then you would note the change in the voltage and the current. And when you compare the emitter bias to the voltage divider bias on at that point, then the key point is more stable, not a lot more stable with the emitter bias, but anyway, the voltage divider bias is more popular because it uses a single DC bias supply. The emitter bias requires a split power supply, so but that's not really a problem anyway. So the voltage divider bias provides a stable Q point, and it's great for AC amplifiers because you can easily avoid signal distortion because the circuit itself is going to establish the Q point, and of course the actual beta, the Q point is going to cause to wiggle just a little bit, but not a tremendous amount. So much less so than the simple bias we looked at before. All right. So here's our circuit. Okay, you can see we have a single DC bias supply called VCC. We have a collector resistor RC. We have an emitter resistor RE, sorry. And we have the two resistors R1 and R2, which form the voltage divider, and hence the name. This voltage here from the remember this is the base down to the ground. This is called the base voltage VB. This is also called the Thevenin voltage, which I'm not going to get into at this point because we don't use Thevenin's theorem. That's one advantage of the shortcut method is you don't need to know Thevenin's theorem. The downside is, of course, it's not. It's an approximate method. It's simply not as good, but it's for our purposes because I've selected the component values appropriately. It's good enough. So you're totally fine to use this method on the test. If you want to use the base current model, you're totally fine with that as well. But anyway, so we can simply say that VB, the base voltage, is the same as the voltage as V2 or VR2. Okay, I think that's pretty obvious. The voltage across R1 is obviously the difference with VCC. We never care about it, so I'm just going to mention it this one time and then never again. Obviously, just look at it. VCC is equal to be the voltage V1 plus V2. Okay, but we never worry about the voltage R1. Voltage R2, the base voltage, is the critical one. The next voltage here is the emitter voltage, VE. Okay, so that's the voltage from the emitter down to the ground. Okay. This is VC. So this is the voltage from the collector down to the ground. Collector resistor voltage, VRC. Collector to emitter voltage, VCE. Okay. Current relationships. Okay. This Actually, it makes a lot more sense to understand this when I use the base current model. But anyway, this is the base current flowing into the base lead itself. The current flowing through the emitter, of course, is the emitter current, and I'm just using conventional current flow here. That is a collector current. As we saw earlier, the relationship between the base and collector currents is given by the beta DC. So we can say then that the beta DC equals the collector current. Okay. Therefore, if we know the base current, then we can say the collector current. Okay. As a general rule, this is going to be in microamps, and that's going to be in milliamps as a general rule. We also saw in our introductory transistor discussions that for all intents and purposes, the collector current is equal to the emitter current. Okay, they're 99.9% equal. Technically, the emitter current is slightly larger because it also includes the base current, but it's very much splitting hairs. All right, so let's do a sample problem. Okay, so we're going to say that R1 equals 20K. And again, it's critically important for you to have this drawing with all the values on a piece of paper as you go through this, because I'm not coming back and flipping slide to slide. I'm just going to, as I've done before, I'm just simply going to solve it, and you need a drawing to look at. So please make a copy. All right. And then we'll let the beta okay, and let's let this be. Let's let that be 16 volts. Oh, sorry. I used 22, sorry. I just misread. Okay. There we go. Okay. All right, so take a picture, write it down, whatever. Okay, just make sure you have it. Okay, so I just have a series of just blank copies of the circuit, and just to kind of make some notes on here. So we want to find the voltage across R2, which is really the base voltage. Okay. All right. If you're looking at any material I provided for you on the base current model, you'll see this called the Thevenin voltage. So it's all the same thing. Okay, so we're just going to use the voltage divider, hence the name. V2 equals R1 divided by R1 plus R2 times VCC. All right, so let's make that a 2, shall we? Okay, so we have R2 was 5.6 divided by 5.6 plus 20, 25.6 times DCC is 22 equals 4.8181 volts. So this is right there, okay? And this is the base, right? The emitter voltage, VE, is 0.7 volts less than the base voltage. So we can say then that emitter voltage VE equals the base voltage minus VBE, which is 0.7. Okay, so we have 4.81 subtract 0.7 equals 4.11 volts. Okay, and that's right. Just running out of room. Okay, that's right there. Okay. All right. The next thing we want to solve for is the emitter current, and the emitter current is equal to the emitter voltage, emitter resistance, and that was 1 k ohms, and that was okay. We said earlier, for all practical purposes, the collector and emitter currents are going to be the same. And now I want to solve for the collector resistor voltage, VRC equals IC actually this is actually one actually. 6.17 volts. Okay. The next two values, which I'm just going to insert a clean slide. Okay. This one is going to be VCE, and this one is going to be VC, which is the voltage from there all the way down to the ground. Okay. So V 7 volts, and I'm just going to write some of this down myself. Okay, all right, next slide. Again, refer back to the drawing. VC equals VCE minus VRC minus equals 15.8 84 volts. Okay. Minus oh, sorry, that was, I thought I did a right number, just the wrong designator. VCC minus VRC. Yeah, that's right. That's from the collector to the ground. The collector to emitter voltage is equal VCC minus VRC equals 22. VCC minus 6.17 minus 4.11. So 22 minus 6.17 minus 4.11 equals, what does this equal? 11.7 2 volts. Collector to emitter. Okay. All right, so I know I have this in a handout elsewhere, but okay. 1, the base voltage. Okay. 2, three, four, 5, and 6. Okay. I think that's all of them. Yeah. All right. Okay, so let's plot the DC load line. And we've looked at this before. So we need to determine the value of IC sat and VCE off. Okay, make sure have the drawing in front of you. Okay. All right. So for IC sat, this is the theoretical maximum current that can flow in this circuit with the given parameters. Okay, so we assume by convention it can never be that, and it isn't that, but this is for the saturation point. We just assume it's 0. Okay, therefore then IC sat, look at the drawing, VCC divided by RC okay, so you got basically 22 divided by 2.5. 22 divided by 2.5K equals 8.8 milliamps. All right. All right, so this is IC SAT, 8.8 milliamps. Okay. For VCE off, assume IC equals 0. Therefore, VCE is equal to VCC, ignoring any leakage current. Okay. And so that's going to be right here. Like that. Okay. Just kind of for scale. Okay. If the Q point was at middle, VCE off would be half, or VCE would be half VCE off, and IC would be exactly 4.4 milliamps, or 1/2 IC SAT. Okay, now let's go in green and plot where we're actually at. We're actually at the IC, which is okay, something like this. So we're pretty close to the center because I picked the values to make it like that. So the actual collector current is 4.11. The actual collector to emitter voltage, which I didn't write down, just recalculated again. So A2 minus answer minus, oops. Okay, 11.72, right? And the advantage with the voltage divider, which using the shortcut method, there's no way to prove this for yourself. So, because we don't take into account beta. Anyway, it's one of the shortcut assumptions, I guess. Anyway, for an amplifier, the Q point can move along this low line like this, as this modulated by the AC. But you want it designed so that it doesn't touch IC SAT or VCE off, because if you do that, instead of having a nice sine wave like this, it's going to clip like this, which is not obviously what we want. But anyway, so that's the I have another one? No. The shortcut method. I've added a few more other things for you here, which let's take a look at. Okay. Okay, so right up here, okay, so these are these are the given parameters. This is the shortcut method results. Okay. Again, the Thevenin voltage is the same as V2, which is the same as VB. This method here uses the base emitter current model, and You can see there's some slight differences, but because I've designed the circuit appropriately to so the shortcut method is reasonably accurate. Um, but anyway, if you look at we're gonna look at let's look at VCE up here, 13.19. Okay, 13.1. It's not much. It's not much. It's not a. It's not much difference. IC is 2.93, 2.96. So as long as you design the circuit well, and you can't just randomly put resistor values in, and that's a little bit too involved for this discussion, then the shortcut method will work reasonably accurate. But but nobody would ever use it for design work, because in order to use the shortcut method for design work, to make it work out and to select good values, you need to determine that using the base current model, so it becomes kind of circular. Okay, so the base current model is the go-to number one best solution method. The shortcut method is really good for troubleshooting in the field. You suspect maybe the transistor is faulty, and you just take some measurements, and you're looking for number around this, right? So that's really where it was intended. It was never intended for design work, but it can be used, as we've just done, just to solve the circuit. If the circuit was designed properly using more accurate methods. So anyway, kind of circular, but okay. Okay, so just another set of problems, okay, for you to work on. All right. What else do I got down here? Okay, so I think I have this handout posted as a separate document, but anyway, this here is the formula summary using the shortcut method. This is essentially just what we went over, so this is a good resource for you. Okay, sample calculation, like that. Okay, another practice question for you. This is an earlier handout I made about 3 years ago on the shortcut method. And again, there's some notes about it. Okay. But I will be in 2023 switching back to the base current model alongside this method. And thankfully, we're getting more in-class time. So I have the time to do both, which is much appreciated. But anyway, that's about it. Thanks for watching. Please spend time looking at this, because you need to do this, know this for when we look at amplifiers the following week. Regrettably, when we look at the AC amplifiers, there's a whole lot of things that we just can't do because we don't know the base current method, because we don't know Thevenin's theorem. And so anyway, it was a temporary decision until we get back in class. It's possible to teach it online. It's just not the best method, I guess. But anyway, if you take a look at my videos on the NPN voltage divider, on the Darlington amplifier, and the common emitter amplifier, for all those things, I use the base current method, long form Thevenin's theorem, right? And you're more than welcome to look at them. I'd be actually glad if you did. But anyway, have a good day, and we'll see you soon. Bye.